Okay, we're starting chapter 11 today, which is on the analysis of variance, or what we'll just abbreviate as ANOVA. So in the last chapter, chapter 10, we analyzed differences between two means. And our hypotheses look something like this. We had mu1 was equal to mu2 as our null hypothesis, and alternative was that they were different from one another. In the chapter before that, chapter 9, we were only looking at one sample, comparing it to some hypothesized value. Chapter 10, we were looking at differences between two sample means, population means rather. But now we're extending this to three or more. So here we're now interested in comparing three or more groups. So that means our hypotheses are going to look like this, where our null is that mu1 is equal to mu2 is equal to mu3. In fact, we could extend this past 3. So 3 is the smallest number that we could have for ANOVA, but this could go out to however many. So I might say equals ... equals mu c, where c is the number of groups. And then our alternative is that the null is false. So what we're saying is that this is not true. At least one of these are broken. That doesn't mean they're all different. So this one could be broken, this one could be broken, this one or this one. All the alternative hypothesis is saying is that at least one of these equality signs is not true. At least one pair of means are different from one another. Now it could be multiple, it could be all of them. We don't know. We're going to worry about that question later. But right now we're just saying the null hypothesis is false. So in this scenario, we have two variables. So two variables. The first is our independent factor variable. So our factor variable, or our factor of interest, it's categorical, and it'll be broken into C greater than or equal to 3 groups. So up here, we were saying 3 or more. C is the number of groups. So the number of groups is simply determined by our factor variable. However many levels of our factor, however many groups of our factor, we're going to say that number is called C, and it needs to be at least 3. And that is what's going to determine our population. And then we're actually going to be looking at a response variable, and it will be quantitative. So we'll be taking means of the response variable. We'll be taking means of the response variable for each level of the factor variable. And what we're interested in determining is whether the means of the response change with respect to which level of the factor variable we are looking at. So what we're trying to answer is, so like our hypotheses, we're trying to answer the question, so are the means of the response variable different across the groups of the factor variable? In other words, does the factor have any impact on the response variable? So let's just quickly look at an example. This is from our textbook. So transportation strategists wanted it to compare the traffic congestion levels across 4 continents: Asia, Europe, North America, and South America. Congestion level defined as the percent increase in overall travel time when compared to a free flow situation or an uncongested situation for 10 cities in each continent. Okay, so I created a box plot. In fact, we'll be creating this box plot in this week's Excel lab. But as you can see, we've got 4 different box plots here, and you can see their labels over here. And the idea is that we have this continuous response. So this response, this is the increase in traffic congestion. That's our response. We're taking means of that. And then our factor would be the continent. And here we have 4 levels: Asia, Europe, North America, South America. So we want to compare the means of the traffic congestion across these 4 levels of the factor. So we're going to call this a completely randomized design. And that's because each observation is randomly assigned to one level of the factor. So you can think in like an experimental setting, if you had 4 different processes, you're going to assign randomly to each of the 4 processes. And so you're randomly assigned to any of the K or any of the C levels of the factor. And so because that's random, we call this a completely randomized design. In this case, we're not really randomizing the cities. The cities are already in each of the continents. So here we're really just taking a random sample of cities in each of the continents. So let's go ahead and return to our hypotheses. So let's talk about the null hypothesis again. So we recall that the null is mu1 is equal to mu2 out to mu c. So what we're saying here is that all the populations have the same mean. So in our example, that means traffic congestion is the same in all 4 continents. And another way of saying that is that the factor has no effect on the response. So the factor having no effect is kind of the key takeaway. So factor has no effect. So in our case, that means regardless of which continent you're coming from, traffic congestion is largely the same. Now let's look at our alternative hypothesis, which is that the null is false, which means at least one population mean differs, meaning that the factor does actually have a significant effect on the response variable. Of course, we already talked about that doesn't mean they're all different. It just means at least one. So if we're taking a look at this, right now it's looking like Asia's the greatest, and it kind of looks different from the rest of the 3. It doesn't really look like these 3 differ from one another, but we'll have to check that formally. So right now it looks like Asia is probably different from the other 3, and it doesn't look like the other 3 really differ from one another. So if we were to reject the null hypothesis, we just need to see which means are actually different from one another. Of course, we have assumptions for performing an ANOVA test. So these should look familiar at this point. So the first, of course, is that they are normally distributed. The population of the response variable is normally distributed for each group. So this will be robust when samples are large. So if you recall the central limit theorem, if you have a large enough sample, your distribution of sample means will be largely or approximately normally distributed. And so we need each of our populations to be normally distributed. The second is that we have equal variance. So the variance of the response is equal for all groups. And if this is true, then we would say that these groups share a common variance. So you can't have one group with this massive variance and then the rest have small variance. That's going to violate the assumption. And the third is independence. So the distributions of the groups are independent. So this is achieved by taking random samples and assigning to factor levels. So if you're randomly assigning to each of the factors, you don't have to worry about independence. That will always hold true. Okay, so in the next video, we'll look a little closer at some of these ideas with our example.